Around the world, teams are working with various solutions for ventilators. Most of them are using the ambu bag, and very few of them have alarms and safety features built into them. Monitoring and protection is critical because patient conditions can change with time, and we need to make sure the machine is working properly. And that's incredibly important for new machines where nobody really knows what's going to happen. Here is the specification from MIT. They talk about a respiratory rate from 8 to 40 breaths per minute, a tidal volume between 200 and 800 milliliters, and an inspiration-expiration period of about 1 to 2, but best adjustable. Assist detection pressure, that means that they'd like to detect when the patient's trying to breathe. And currently we don't have that. Airway pressure should be monitored, and an absolute maximum pressure of 40 centimeters of water. The plateau pressure should be limited to 30 centimeters. This is the maximum pressure when the breath is being blown in or the air is being pushed into the patient. A mechanical safety feature as an ultimate protection for the patient. Having the basic specifications now from MIT, the question is, can a stepper motor do this work? Do we have enough power? And can it deliver the amount of air at the pressure we need? And the short answer is, after a little bit of maths, yes it can, at least in theory. The stepper motor can deliver a force of about 50 newtons, and in theory we need about 24. So we have a good margin, and as we're only using it in one direction, we could even put a weight on there to double the force if necessary. But hopefully that won't be the case. So now we need to find an old printer and then convert it to the ventilator. Here we can see the outlets and the inlets for the air pressure gauge, and the air pressure gauge in more detail. We can see the monitor connections and everything we need for the safety features to limit the maximum pressure in the tubes. Here are the bellows. They are made from some flexible ventilation tubing, 100 millimeter, and they're powered by the X direction stepper motor. The black brackets you can see there stop the bellows going sideways and keep them in their place instead of using a big tube that other people are using. This reduces the amount of wear on the bellows and stops them slipping and sliding. There's a string there, and the function of the string is that when the motor pulls back to take in air, that the bellows are evenly pulled out and we don't have very large stretched pieces and less stretched pieces. The controller is a standard Arduino Uno. It's really actually overpowered for this. We can adjust the air volume, the respiration rate, and the ratio between inhalation and expiration using potentiometers. And currently we have no display or anything like that, but we can do it later. So the question is, how does it work? And the answer is quite well. I hadn't expected it to be this good. You can see the spacers and the supports for the tubing holding it under no pressure, so it's all going in and out quite nicely. This is naturally, of course, with no pressure, so there's not really a lot of work happening with the bellows at present. We're going to put my thumb now on the tube to create some pressure. I'm going to partially block it. You can hear now the air going in. And now a little as the air goes out, and you can see with a constant pressure of about 10 centimeters it's working nicely. And the bellows are not having any problem at all here. We've got 20 centimeters, and again the bellows are looking quite comfortable. The black supports are holding everything back in place. Remember, this is all with self-printed parts, including the valves. Going up to 25 centimeters of air. This is now close to the limit of what we want to do. The maximum pressure under any condition would be 30 centimeters according to the MIT specification. Here is a video showing the limited torque of the stepper motor and how it then misses steps. In slow motion the pressure builds up and then it comes to overpressure and the motor just jumps back. When it goes back onto reset mode, Here you can see the pressure gauge again and the two, the various needles in it with wires. So as soon as the water or the liquid, an ionized liquid, touches these, then the Arduino knows there's water there, and we know what the pressure is. The great thing is if the pressure goes too high, then the water would be pushed out the top of the tube and automatically limit the maximum pressure. There you can see the maximum pressure limiter and the alarm. It's a simple concept. You can see the stepper motor used to push a 3D print head, and now we're just pushing bellows backwards and forward. Here's that all-important pressure sensor and monitor. You can see we've got 4 needles on it at present. We've got one at 0 centimeters pressure water level. We've got one at about -5. So if for any reason water leaves or there's too little water, then we will detect that and not deliver an overpressure to the patient. We've got one sensor at 30 centimeters. So if the pressure goes too high, then we can reduce the speed. And then we've got one needle right at the very top. It's about 40 centimeters, so that's in case there's a real emergency and that's a complete shutdown. Something's gone wrong with the system. This should never happen, but it means there's a failure, and so we shut down and make sure that nothing happens to the patient. One of the aims of the project was to see if using parts from the 3D printer, we could in fact then print enough parts to be able to make a useful respirator. And I think we managed to do that. We're using valves just made with TPU and PET or PLA. And for the pressure level sensor, we're using a standard syringe with some wire inserted into it. An Arduino connector crimped onto the end. This is pushed into the syringe and then finally crimped at the end, so it's a good electrical connection. This is a standard part, easy to make, reliable, and no shortage of components.